The first group of charts we'll look at covers a fairly wide spectrum of what are probably the most commonly used set of charts. Line charts, bar charts, column charts, and scatter plots are probably the easiest charts to build and understand due to their relative simplicity and their common use even as early as elementary school. Each of these charts simply shows a data point at a specific point in relation to each axis. Since we've already created a bar chart, let's start there. Bar charts function with one-dimensional series where each references a set of unique values for a set of categories. As you can see in this chart, the result is that we get a bar with a different length for each assigned category. The order of the data points matters because the order defines how the chart points are classified. This will not be the case for all charts, but it is an important component to single-dimensional chart types. Bar charts also come in a couple of different flavors. The type that we're using right now is of the 2D class. Within the 2D class, there are three types of bar charts: the clustered bar chart, the stacked bar chart, and the 100% stacked chart. Each chart interprets the series data slightly differently, so let's look at some different charts to understand what these differences mean. The chart we're looking at right here is a clustered bar chart, and it simply lines each data series up next to each other. For comparison, this chart type is great for looking at how two different values that should be similar compare. For example, here I have test scores for 3 different students across 6 different exams, as well as the average for the class. You could place each of the 3 students as data series and use a clustered bar to compare how they've performed against each other and against that class average. As you can see, you can quickly identify above average and below average performers, and you can have alternative views. For example, I could look at the groupings by person and see how their scores differ across different categories. This can all be done very quickly and easily using the Switch Row and Column command on the Design tab. The stacked bar chart takes each of the series components and adds them together to show how each contributes to a whole. Say that you're running a company with 3 different operating units, alpha, beta, and zeta, and you're looking at the total company revenue. It might be useful to see how these components break down over time to see how the business is shifting. Graphically, each of these lines represents the total for all of the data series included in the graph. Not only do you see how the total revenue is changing based upon the full length of the line, but you can also see the contribution from each of the underlying segments based upon the color component of the line. In this example, you can see that unit beta has varied somewhat, increasing its component over time, while alpha and zeta have basically replaced each other, resulting in somewhat steadily increasing revenues. The stacked 100% bar chart is a slight modification to the prior chart that frames each contribution as a fraction of 1. Each line will add up to 100% no matter what, and the color indicates which component contributes what percentage. As an example, if you look at the bottom row, you can see that alpha contributes just over 60% to year 1 with a revenue of $125, but beta contributes less than 50%. And then for year 6, you can see that the beta contributes over 60% and zeta contributes less than 40%. Each of the 3D bar charts are identical to the 2D versions in interpretation, except they provide a slightly flashier view. I can walk through each of these and change them to the 3D view by simply going to the Change Chart Type and picking the appropriate chart type to switch it to. The same information is displayed, it just gets displayed a little bit differently. The choice to use bar charts versus column charts is largely a personal choice as well, since they are easily interchangeable. Column charts come in each of the same categories as well, with clustered, stacked, and 100% stacked. The only difference is that instead of being aligned vertically, they get aligned horizontally. Line charts are a slight modification to the column chart approach. Rather than creating a column out of a value, a single point at the top of where the column would be gets set, and then lines are connected to each point to develop the graph out. Line charts can be defined with or without markers, where markers simply indicate where the observed point is. The difference is entirely visual, however, I often find the markers to be helpful. Line charts have 3 functions that are identical to their column chart brethren. The standard line chart is like a clustered column chart where each value is plotted independently and then the lines are connected. The stacked line adds them together to show how the whole is moving relative to the individual components. Here you can see that the whole is represented by the gray line, as that is the blue plus the orange plus the gray data. The stacked 100% line does the same thing, except it sets its total to 100%. So you can see that the blue line starts at 60% and ends up at 0%. But when adding the blue, the orange, and the gray, you always end at 100%. These charts are most often useful for looking at how they change over time. For example, when we look at our test results in a line chart format, it doesn't make much sense and it doesn't assist us in making any conclusions, as there's no real relationship when going from algebra to English or from biology to U.S. history. Comparatively, plotting the revenues by operating units on a line chart helps to show us how the revenues are changing over time. Each chart has a different value. The standard line chart shows how each unit performs on its own. The stacked chart gives us an idea as to how the total is changing, as well as the directional shift of the underlying units relative to the total. And finally, the stacked 100% chart shows us how the changing percentage distribution occurs. Line charts can also be converted into area charts quite easily, and there are area charts representing each type of line chart. The basic area chart simply draws the line chart and then fills the area in between the x-axis and the plotted line. For our dataset, that chart isn't usable without making most of the series semi-transparent, which I've done here. The stacked area chart is very similar to the stacked column chart, except on a continuous type of scale. Each additional series gets added to the top of the previous line to see how the total is made up of the individual components. You can see the share of the blue decreasing, the share of the gray increasing, and the share of the orange generally remaining unchanged with a slight increase. This can be valuable for looking at how the individual component share changes over time for large time periods. Finally, the stacked 100% area chart corresponds to the 100% stacked lines and 100% stacked columns. The total gets set at 100%, with each individual component being filled in with the color that makes up that percentage. So for this gray at the very end, since the height goes from 70% to 100%, that means that approximately 30% of the revenue is contributed by unit zeta. Each of these also has a 3D look to give your charts a little bit more of a wow factor. Line charts are pretty common and very easy to understand, but sometimes they're not quite enough, as each data point may be lined up based upon a different order. The final chart I'll cover in this lesson will be the scatter plot type. The scatter plot is our first two-dimensional chart type, so let's look at a series. Instead of a name in a series, the series has a name, an x values, and a y values. This is important, as now rather than simply plotting each point's value over equal intervals, you've also got to define the location along the x-axis for where to plot the data. Suppose, for example, that the revenue information that we had for our 3 operating units was spread across different points in time. Here's our standard line chart, where the line chart implicitly assumes that each one occurs at the same point in time. On the right, I've used a scatter plot with smooth lines, where the zeta data was reported over a time frame of every 6 months for 3 years, the alpha was reported every year over 6 years, and the beta data was reported every 2 years over 12 years. By defining both the x-axis and the y-axis of a scatter plot, we can create line charts that reflect differences in both the y and x values. So that's how the data looks, but our example is poor for applying scatter plots, so let's take a step back and look at our different scatter plot types. There are 3 basic types: the simple points, the connected points, and the bubble plots. A simple scatter plot looks like this, where each value from the dataset is laid out on a chart. Where a bar plot gets really messy with dozens of bars, a scatter plot can easily display the same type of information by comparing individual points along a line. For this chart, I've plotted 15 different students and their performance across 6 exams as compared to the average. While not a perfect view, since the x-axis does not show the test names, lots of information can be presented in a condensed space and for looking at correlating factors. For example, we could plot our revenues for each of our 3 operating units based upon the number of employees working, and see how each correlated to revenue. This shows us how relative changes in the number of employees translated into differences in revenue. Adding the line component makes it somewhat more useful, but scatter plots with lines come with a danger whereby introducing the line dictates that the order of the data points now matters. This set of data points has been ordered by employee count, but what if they're jumbled out of order? The scatter form of our plot looks unchanged. There's no discernible difference from before. But once I add the line, suddenly our chart becomes completely unreadable. I use scatter plots quite frequently for looking at variance analysis and residual plots, very statistical pieces of information. Otherwise, I also find them useful for mixing and matching data across different x-axes, as we've done with the employees here, so long as it's done carefully. The last type of scatter plot is the bubble plot, and it will be our first three-dimensional graph. So let's dive in and look at a series entry. As you would expect, a three-dimensional series has three entries: an X entry, a Y entry, and for the bubble graph, a bubble size entry. Most three-dimensional series will have a special name for the third entry to make the value clear. This chart generates a scatter plot where each of the dots gets a custom size. In this case, I simply made the spots change in size based upon the ratio of employees to revenue. Bigger circles mean a higher revenue per employee, while smaller circles mean less revenue per employee. Such graphs can be interesting and useful, and making the series semi-transparent can help in identifying overlapping points. As you can see, unit zeta's high level of revenue per employee nearly hides the unit alpha amount at 3, while the unit beta completely hides unit alpha at 2. We'll cover some of the more common customizations in more detail later this chapter, but for now you can see that I've simply used a transparency setting. Finally, the bubble chart also comes in a 3D variety. This can be neat looking, but it provides no real additional value. And for this example, I think it actually obscures the chart a little bit. This completes our coverage of the bar, column, line, and scatter plot charts. In our next lesson, we'll dive into the surface charts and radar charts.